This is the fifth video in a series of videos on getting started with CPN tools. In the last video we took a look at editing CPN models, and in this video we'll take a look at analyzing models by means of state space analysis. Now I've loaded in the protocol we made last time, and let's try and do some state space analysis on this model. But before we start, I'll show you something. So if I execute the send transition, I continue adding tokens to the place A. I can continue doing that. This means that this model has an infinite state space, and I can get an unbounded number of tokens on the place A. Normal methods can't handle that, so we need to somehow restrict the number of tokens on the place A. We'll also have the same place tokens on place B, C, and D. In order to fix that, we'll impose a limit on the network. So basically we're going to introduce a capacity of the network, and every time we produce a package on the network on places A, B, C, D, we consume a token from a capacity. So let's go and create a place to contain the capacity. What type should this place have? Well, we're just going to use basically black tokens. That's tokens that are not distinguishable. We don't have a color set for that. So let's go and create a color set for that. We create a new declaration. And the set of black tokens is in CPN tools called the unit color set. So we just go and say this is type unit, and we'll go with a capacity of 2. That is, there can be at most 2 packets on the network. Now when we transmit a package, well, we should consume one from the capacity. This. When you transmit a packet, well, if we successfully transmit a packet, we just move a package from A to B. So we really don't change anything. But if we transmit not successfully, we actually produce an extra space on the network as we consume a package from the network without producing a new one. So we should conditionally produce a token on the place here, depending on the value of the OK function. So we're going to create an arc from the transmit package to capacity transition, and we're going to clone this description because this is almost what we want. So we need a bit more space. Okay, so if OK, then we don't want to transmit anything, so we want to produce empty, the empty multiset. And if we don't successfully transmit the package, we produce a single unit value, like this. Okay. And when you transmit an acknowledgement, the same thing happens. So we can simply go and clone this arc, like that, with the inscription down here. And when we receive an acknowledgement, we unconditionally consume a package from the network without producing one. So we produce a token like that. So now when we transmit, we can only transmit 2 packets, and transmitting across the network, we still can't send a new package, receive the package, transmit the acknowledgement, and receive the acknowledgement, and now we can continue sending the next package. And this ensures that we at most have 2 packets on the network at any one time. This is also actually more realistic because this signifies that the network has a physical capacity. It can only handle so many packages at once. Okay, with that out of the way, let's try and do some state space analysis. So we drag out the state space tools. The state space tools basically consist of a 4-step rocket every time. So we start by entering the state space tool. What we see down here is we get an error. The reason we get an error is that all nodes must have a unique name in order to enter the state space tool, because we need to be able to refer to the nodes in state space queries. So they need unique names. And I have a place here without a name. So let's give it the name capacity. And now I can enter the state space tool. Just to show you what happens if we have places without a unique name, let's try and change the name of this place to A. So now we have 2 places called A, and they get a slight red glow. It's not as colorful as the glow you get with an error, but it's just a warning saying you should probably try and change the name so you can do state space. Okay, let's disband this error message. Now that all places are named and uniquely named, let's enter the state space tool. And depending on your computer, this may take a short while. You get a green box down here signifying we have entered the state space tool. The reason we need to especially enter the state space tool is that CP/M tools generate model-specific code for generating the state space more efficiently. Now we want to actually calculate the state space, and this takes, in this case, just a few seconds. Then we generate the strongly connected component graphs, which is used for many analysis. And finally, we generate a standard report. The standard report contains a whole bunch of interesting things we can look at without having to write a single query yourself. So we just save the report, and we get a green bubble down here saying that this has been saved. Having generated the report, let's take a look at what it says. So this is the state space report we just generated. We can see the number of nodes and arcs in the state space. It's not too big. How much time was spent actually generating the state space, and we can see that the status is full. That is, we have generated all the states of the state space. If we get a status saying partial, it means we couldn't generate the entire state space, probably because we ran out of time, or because the state space is infinite. We also see some statistics about the strongly connected component graphs, and we can see it contains less nodes than the state space, but it contains more than one node, meaning that we have non-trivial strongly connected components. Then we get some bounded properties for all the places. We can see, interestingly, that the integer bounds, that is the maximal total number of tokens for the places A, B, C, and D, are in all cases 2, which makes sense because we actually limited their capacity to 2. We can go and see some multi-set bounds. We can see some home properties. We can see that the marking 1473 is actually a home marking. That is, we can always reach this marking. And we can also see that the same marking is a dead marking. That is, it has no enabled transition. Also see we have no dead transition instances and no live transition instances. And we can get some fairness properties, and we can see that in order to have an infinite execution sequence, we must always send a package and transmit a package. This means that in order for this protocol not to terminate, we must continuously send a package and unsuccessfully transmit the package. And if we have a finite sequence, we will end up in state 1473. So let's expect this state 1473. So we go back to CP/M tools, and we take the state space to simulator tool, which allows us to inspect a state from the state space tool. So let's enter 1473 and apply this tool to the background. And we can see we certainly have no enabled transitions. We knew that, it's a dead state. And over here on receive, we see we have received the end-time message, signifying that this state is in fact the one where we have transmitted our packet successfully. So this is kind of a nice property of the protocol. We can also go and investigate the structure of the state space for this.